Yes, so I'm here and I will share the book with you now. So you should be able to see it now. Chapter 24.3. But anyway, like to make this meeting shorter, I will start as usually with my notes, and when they will end, we will go directly through the book. So I propose to start from the very beginning. So let's just make a quick overview of 24.1 and 24.2. So 24.1 subchapter was about tension between relativity and quantum mechanics. And basically the main thought there was that if we add relativity to quantum mechanics, we will get antiparticles and it will lead us to the fields picture. And a few more thoughts about QFT was there, that QFT is inconsistent mathematically actually, and some tricks are needed to overcome those problems. And yeah, and actually if we can overcome somehow the tension in the mathematics between relativity and quantum mechanics, then we get a really precise theories like standard model or Dirac equation. Probably Dirac. Okay, so
Slav, I think maybe your microphone sensitivity is slightly low. You cut off sometimes between words.
Okay, 1 moment. Is it better? Like 1, 2, 3, 4, 5.
Now.
What?
It sounds fine for the moment.
Okay. Okay. Yeah. Please notify me if it will happen again. Okay. So, and the next chapter was about like why antiparticles imply fields. So, and in that chapter we kind of accepted the view that we need antiparticles, and we will see basically when we will get to the Dirac equation why antiparticles follow from the relativistic quantum mechanics. And if we believe in the need of those, then we will need to believe into creation and annihilation processes, which are connected with conversion of the energy to mass and vice versa. And therefore, like the number of particles in the system can dynamically change. And that is why we need fields to be introduced. So
I'm afraid it still happens.
And does it happen for anyone else?
Yeah. And also there's an echo.
Yeah, we had that feedback loop last time. It's only when he's talking.
Sorry. I think I got why we have that problem. 1 moment. And now?
So much better.
Yeah, sorry. I forgot when I got back from the village, I forgot to switch the microphones in Discord. So I was speaking in the on-table microphone, and the one which was working was the built-in one. So sorry. Okay, so I hope sound now is much better. And that's
no cut-off.
Yeah.
No cut-offs either.
Yeah, great. So, okay, I've been talking about the annihilation creation of the antiparticles, and that implies that we will have systems in which number of particles can dynamically change, and therefore we will need fields, and to think about particles as the excitations of those fields. But actually we will talk about that in chapters 25-26 later. So basic thing here is that if you have like energy to mass conversion, it means that if we have enough energy we can create a particle, and we also need for the quantum numbers to be conserved, like charge, for example, or mass. And therefore, we will need antiparticles to be. So antiparticles is kind of answer to the energy to mass conversion and also conservation. So it's kind of it. Yeah, and here we come to the energy positivity. So we can suppose that our system has some definite energy and corresponding eigenvector to it, some psi, and it will mean that like h of psi equals e of psi, and we get that state after a measurement basically. So we can have some solutions for the Schrödinger equations, which will be just exponents. You can see time in there, and some functions c of x, which will depend only on the position at the front of the solution. It's important for us to have energy positive, and to be precise, actually, it should be bounded from below, because we can renormalize everything to make it positive. So if we could have kind of negative energy, it will mean that we have kind of really big, deep well in energy terms, so infinite well actually. So we'll have some kind of like catastrophe when everything will collapse into there or something. Yeah, so we will have kind of catastrophic instabilities in there. So now we can reconcile the definition of positive and negative frequency parts, which we discussed in chapter 9, where we have seen like that those had kind of opposite powers included. That was done because in reality we were talking about sign of the energy. So I will show you the formulas from chapter 9 just to recall it better. Yeah, it is there. Let me zoom in a bit. Yeah, so if you recall the Laurent series in there, you can recall that like our complex function f capital could be kind of separated in two parts. One is called f minus and another one is called f plus. And you can notice that f plus, called positive frequency, has only negative powers. So it was kind of confusing while we were reading chapter 9. But now we know that we call it positive from the physics perspective. So it is positive because in those negative powers we have positive energies encoded. So basically those 2, 1, 3, they are just energy levels. And vice versa for f minus, we have positive powers, but in physics we will have, like in the solutions of the Schrödinger equation, we'll have minuses here, so minus energies are encoded there, like -2, -3, -1, etc. Yeah, and we had something like this for a function description. Basically, like we could describe that function on a Riemann sphere. We kind of had for the Laurent series the annulus, which looks like that in the complex plane. So that's kind of really interesting connection between mathematics and interpretation of the wave function in terms of the energy eigenstates. Yeah, so let's go back to the summary. And it means now that we have a physical reason for that notion. And every function, wave function, psi, could be expressed in terms of energy eigenvectors basis, and each eigenvalue should be positive there. So psi of t should be positive frequency function. And it is a deep, subtle, and mysterious relationship between math and physics, actually. So Penrose kind of, I think, concerns it like a really beautiful one. And at the end of that subchapter, it finishes with the statement that in non-relativistic quantum mechanics we have no problems with energy positivity, because momentum in there could only have the positive values. So we will have problems only when we add relativity. So in non-relativistic quantum mechanics, eigenvalues for the corresponding minus Laplacian operator will always be positive. Now we can have like a small break, maybe some questions about 24.3. Okay, if none, let's continue with 24.4. And here we have like the difficulties with relativistic energy described in like more informative terms. So let's take a look at the relativistic energy. And relativistic energy looks like that. So you can see probably the square root here, right? And it secretly includes non-relativistic energy, p squared over 2m. If we will take a look at the Taylor series expansion of it, you can kind of find it in the on Wikipedia, for example, yeah, or in other sources, in the other sources. I think we have seen that in chapter 18 while talking about that, so maybe even in our past videos or recordings. Okay, so, but we can't use that expansion as our Hamiltonian because the classical series will not converge for some values, and if we will think about using the square root expression, it will also has its problems. So, but at first let's set c equals to 1, just to simplify the expression to rest mass squared plus p squared and square root over it. So what are the problems? So the first problem is that we can notice that in quantum mechanics p squared is operator minus h bar squared. I haven't h bar sign, so I used h there, sorry. But it's h bar actually. So we need to take a square root of that operator, and kind of what does it mean to take a square root of the operator? That's the first problem. Another problem is sign ambiguity, which means that when we will add quantum mechanics, it will generate even more problems, because while acting on the complex functions, we won't be able to say just like take the positive root there. We will have like nth roots of unity, right? And they will be kind of on a complex circle. Yeah, and like overall square roots function will be kind of, as we have seen in the Riemann surfaces chapter, it will be like two-leaf surface basically. So it's not so easy to work with the complex square root. And if there is and the third problem is that if there is possibility for something in quantum mechanics, then it will have an impact and could happen eventually. And therefore, we open to the possibility for the negative energy values. And as we have discussed, it gives us a catastrophe in terms of physics. So, in overall, in the non-relativistic quantum mechanics, there are no square roots, so we have no problems. And in relativistic quantum mechanics, for one particle system or non-interacting many particles one, we also will have no problems. But if we will have relativistic quantum mechanics plus some interactions, even for a single particle in the electromagnetic field, we will get a chance to get negative energy results. So that's kind of the first example where we kind of begin to perceive the tension between quantum mechanics and relativity. We got into some problems, and we will see in 24.8 how those problems could be resolved. And the basic plan for it is to get rid of the square root, get Dirac equation, then obtain the original point on the negative energies elimination, and got at the final to the antiparticles also. So we should ask now, what is the essential feature where our square root originates? Any question about the 24.4? So the next subchapter is about non-invariance of the time in relativity, basically. So sorry, I see that video for some reason lagged. Give me a minute to take a look why. Yes, sorry for pause. I don't know, had some strange glitch in the equipment. Okay, so 24.5. And 24.5 is about the non-invariance of d by dt. So we know that in relativity we have like a space-time mixture, so space got mixed with time, and therefore in relativity we need to have kind of symmetry between time and space, and therefore d by dt by itself will not be invariant, like kind of preserved, and d by dt is kind of the main ingredient in the Schrödinger equation, and it comes in there from the quantization trick, which shows its link to the energy, and therefore it is directly linked to the non-invariance of the energy in relativity. And we know that in relativity energy is mixed up with the momentum, and one more thing which is not invariant in there is mass, and mass is additive and conserved quantity, but it will be higher because it's not the intrinsic mass, not the rest mass. It's the mass which we will measure in some other reference frame. So the larger the velocity of the particle, the larger the relativistic mass will be. And mu here is the rest mass, which is invariant in relativity, but not additive and non-conserved quantity actually. So, and we can kind of have that equation for the rest mass. So rest mass equals m squared minus p squared. It's the same equation of the relativistic energy from above. So where we have like m squared c to power of 4, but we have c equals to 1 here. So we have no speed of light in our formulas here. But nevertheless, we may toy around with using the rest mass instead of the mass to get new Schrödinger-like equation. And if we will try to quantize the rest mass, we will get IH bar squared times the operator, and the operator is this one, which is called the Lambert operator or wave operator. So basically it's Laplacian in the Minkowski space. You can see the same Minkowski metric used here. So we have like positive 1 near d by dt and minus 1s for the space coordinates. And we can write the equation above in the form of...
I have a question.
Yeah?
Do you know what the missing symbol is there? I assume the square should be a wave function, or the square in front of the equal sign.
Yes, square.
I assume that's the symbol that's missing.
No,
the
it's
very first character.
It's not a missing symbol. It's not a missing symbol. It's the symbol for the wave operator. It's box symbol.
Yeah, I thought the same thing, but then if you Google Klein-Gordon operator, Klein-Gordon equation, they'll show you that this like Lambert operator, or whatever they call it, is actually represented by the box, which I also thought was. I thought the same thing as you, that hey, there must be a misprint here, and like there was a symbol that got replaced by the box, but it's the real symbol.
Yeah, and actually,
I looked at the wrong place apparently.
Actually, I think I'm not sure about that, but I think that those missed symbols you're talking about, they are kind of rectangled. They are not squared. I think it seems to me that they have more squashed form.
Probably depends on typeface, but probably something.
Yeah, but it's easy to kind of be confused seeing the box. But box is a genuine symbol for the operator.
And the name of it was Lambert, or?
Yeah. Lambert Operator. Lambert.
Okay, great. That's all cleared up now.
I was just going to say one thing. I heard one kind of cute interpretation is that the nabla is 3 variables, x, y, z, so it's a triangle. But the D'Alembert is 4 variables, t, x, y, z, so it's a square. I don't know. It's a bit silly.
Yeah, it will be harder and harder. So I think it's pretty great to have a circle in there. I mean, for infinite dimensions.
Oh,
yeah.
All right, sure.
But it will be hard to draw the octagon, for example. Okay, so basically we can rewrite the equation above with the rest mass. I mean, the scene where squared rest mass equals to mass squared minus p squared. We can rewrite it, rewrite it into this equation, I h bar squared times D'Alembert operator, so it's like a left hand side of it, and another hand side of it is mu squared, so we can multiply it by the wave function and get that equation. And afterwards we can rewrite it in this form. So it will be like squared plus m capital squared, and m capital in there is just rest mass divided by h, I think. So it's kind of just mass divided by some constant, and that equation is called Klein-Gordon equation. And Schrödinger was actually the first one who got it, but he settled afterwards with his non-relativistic variant. And modern QFT field theory uses Klein-Gordon equation to model mesons, spinless massive particles. But the times Dirac was working, when Dirac was working on his equation, there was no QFT. And he was kind of aimed at for the d by dt operator in that new equation, but also he wanted for it to be relativistic. So he kind of wanted to transform Klein-Gordon equation somehow into Schrödinger-like equation. And his reasons behind that line of thought was that we have the requirement for the wave function to be a probability density, and that meant that like modulus squared of the wave function should be positive definite thing. And this is another similar request for the positivity, like energy positivity, but it is not quite the same. And both of those will help us later to prove CPT theorem, I think in chapter 26, but I'm not sure, or maybe 25. Yeah, in 25 we'll talk about, like parity and time reversals, so maybe even in 25. Yes, so that's it. Basically what we got here is the Klein-Gordon equation. And now we want to have d by dt there instead of double derivative of time. So the question is how to do that. And now we come to the subchapter number 6, which is called Clifford-Dirac square root of wave operator. So Dirac had D'Alembert operator and a wish for d by dt. He took a square root from the operator and got those delta i's. And actually, I suggest you to take a look at the video, the first link in chapter 24 channel. I have sent it's kind of 2-minute video, and it shows the basic reasoning behind the like how Dirac actually derived those deltas. Like he kind of assumed that they were numbers at first, but then he proved or kind of got some anti-commutativity relations, and therefore he understood that they shouldn't be numbers, and he tried some matrices. And that's kind of how he hacked the system there. So I think his road wasn't so straightforward as it is stated in the Penrose book. Yeah, but anyway, he kind of got those anti-commutative operators, which, as we will see, describe how spin degrees, like new degrees of freedom for the particle spin for the fermions. And now we will talk like in details about that, like how to take the square root. And the theory of taking square root of Laplacians was really well prepared even by Hamilton and Clifford, but Dirac didn't know about it. And Hamilton and Clifford knew that you can take a square root of the Laplacian by using quaternions, for example, in 3 dimensions. So it will look something like that. And this work wasn't well known at 1920, even to specialists in algebra. And actually, I put a small note from me here that it seems that many people nowadays are yet unaware of it. And by this, I mean that they are kind of not aware of the geometric algebra as a possibility for like a kind of a new language for the doing calculation in mathematics, which kind of unites vectors, b vectors, 3 vectors, and kind of unites geometry and algebra in one thing. So we will talk later about that. I mean, in a few weeks. And anyway, such entities like those deltas, oh sorry, not deltas, it's not deltas, it's gammas, right? So it was gamma matrices. Yeah, so those gamma matrices are really important in physics. And by gamma matrices here, I mean like in general elements of Clifford algebras actually. So, and in Dirac's case, the elements, we have the Clifford algebra 1-3, and 1-3 is its signature. So it's kind of the Minkowski-Clifford algebra. And in there, we will have the Clifford basis consisting of 4 elements, which and they are squared could have will have the same signature as the Minkowski matrix, basically. So like gamma 0 squared is 1, and all the other gammas will be -1. And also they will have the anti-commutative relations. And secretly, it is because every of such gamma will correspond to the space direction. So the 0 gamma will correspond for the time direction. Other 3 gammas will correspond to the spaces directions, like 3 directions, and those gamma I, gamma j products will correspond to the planes. So all that anti-commutativity relation is just it just means that if we will reverse the product, geometric product kind of 2 vectors, we will have orientation reversed of the plane. So it's kind of reverse of the normal, but yeah, you can think about it simplified, just as anti-commutativity in algebra. Anyway, by using the same thing as we have seen with quaternions, now we can define the operator called Dirac's operator, which if we square it, we will get the D'Alembert operator actually. Yeah, and here is just like a few equations with those gamma. And in the second one, you can see that gamma, like 3 gammas were kind of condensed into scalar multiplication between it and the 3-dimensional Laplacian in there. So we also have the slash notation, which was proposed originally by Feynman. And with this, we can do or like condense that expression even more. So we can mark that expression in the brackets as D slashed here, and therefore that D slashed will be just like a scalar product between gammas and the d by dx A. So we will condense everything here to the like 4-dimensional scalar product. And for any vector A, we can get a Clifford algebra element using the same slash notation, just by multiplying its values by the Clifford elements. So therefore we will have some element of the Clifford algebra. So, and like just a note about Clifford algebras, you can go back to the chapter 11 or just listen to me now and believe that in Clifford algebras, all we have is just the reflections actually. And therefore that element will correspond to some kind of reflection, I think. So yeah, and if you will have like more powerful Clifford algebra elements, for example, with second power of gammas in there, you will have some kind of rotations or planes. So basically, you will have some kind of geometric structure in there, codified in algebraic way. Any questions about the previous subchapters? I mean, 5, 6, maybe 4.
No, he has the comment that that's correct, that the gammas correspond to reflections, and if you compose two, then they correspond to a rotation, like you said. Which we read in the epsilon group recently.
It's what?
We touched upon that very recently in the epsilon group.
So, yeah. Thank you. Yeah. Oh, yeah. I think
Also
that when I will make some small presentation about geometric algebra, we will see in there. Actually, I have a notebook here where I already started to write something about geometric algebra and spin. So you will see something like that in there. So I will show you how the reflection, like you can interpret your vector, 3D vector, as a normal to a plane along which you can do the reflection for the another vector, for example. And you maybe can recall that in chapter 11 we had the rule about the great arcs on the sphere. So I kind of not really good at drawing things. So I have like a half of sphere in there and like zoomified view of a patch. And we have like a center of a sphere, 3 vectors going on into the sphere here, like radial ones. And we have like 3 rotations, like U1, U2, and U3. And actually Clifford algebra and geometric algebra shows us how to justify the statement by Penrose that we can have like triangle addition of the rotations on a sphere done by the half angle rotations. And actually we have already seen something similar in, I think it was chapter 22, when I was preparing for you a small slide about Bloch sphere. You can find it in the chapter 23 chat. Let me take a look. Maybe I have it in my Telegram and I will be able to show it to you. No, I haven't saved it. So anyway, like in the Bloch sphere representation of the spin 1/2 particle, you could remember that we had that strange property that angles were divided in half. And you can justify it by considering the reflections and rotation connection, basically. So like reflections are connected with rotations in the similar way, so the angle is kind of halved in two. And that's why quaternions describing the rotations are also halved in two in their polar representation. And actually, like one more point to add here, like geometric product is just the product which is the sum of the scalar product and wedge product. So you can obtain here from 2 vectors a scalar plus some like higher graded algebra structure, maybe plane, maybe cube or something. And and scalar product actually is also could also be not only the scalar, but it could act as like interior product. If you remember the calculus of the differential forms, we had like a collapsing operator in there where we can collapse. So basically scalar product is the thing which will collapse something like in dimension. And the wedge product is the product which give us the growth of the geometrical structure. But anyway, you can see that we can kind of, by using Hodge duality, we can interpret, for example, the plane as I multiplied by the vector product in here. And I here is a special thing called pseudoscalar, like the maximal element of the algebra. So we kind of can reinterpret that wedge product in terms of the pseudoscalar and vector product. And we will have kind of similar, a lot of similar equations in physics and mathematics. We have seen those when we talked about, for example, polar form of the complex number or polar form of the quaternions. And there is really similar equation for the Poly matrices. So if you take a look at the theory of the Poly matrices or Pauli, then you will see something like this, like sigma basis with the Pauli matrices is multiplied by some other vector A, and it's multiplied by another sigma over B, and you will have like identity matrix multiplied by A, B scalar, and here you will have like sigma by vector product and also I. And it's actually transitions really smoothly to the geometric algebra where we can reinterpret those matrices in terms of the directions instead of just like operators acting on the wave function. So, but that's kind of another story, and we will talk about that a little bit later. Okay. So my notes ended, and let's go for the book. Okay, 24.7, the Dirac equation. So what we have here. First of all, let's go back to the Klein-Gordon equation. And now we can just write, instead of the Lambert operator, that Feynman's operator or Dirac operator squared, and therefore we can like factorize that that equation into two brackets, like d minus im plus d plus im, where m is mu over h bar. And therefore we will have, by just like equating that with 0, we will have two equations. The first one is called the Dirac equation for the electron, and it is the one with the plus sign bracket. So we will have this expression for it with minus on the right. And by reinstating the h bar, we can write it in the terms of the rest mass, and we will get something like this. And you can see that it's kind of more familiar now in terms of like one derivative here to the Schrödinger equation. And actually, we also get the similar equation, which is called Anti-Dirac Equation for the like anti-electron, from the another bracket with the another sign, like plus sign here. Yeah, and that will refer actually to particle with the negative mass minus hm capital. Okay, and yeah, and what we have here is that we can rewrite that equation, the original Dirac equation, in a more similar form to the Schrödinger equation, and it will look something like that. So we have the same IH bar here, d psi dt, and that complicated expression here. And this expression kind of plays the role of the Hamiltonian operator in the relativistic quantum mechanics. And of course, singling out the operator d by dt is not relativistic invariant, but the overall Dirac equation is relativistically invariant, so therefore this one will work nicely in the relativistic case. Okay, and now we came to the kind of really interesting part where like it was historically a considerable shock for the physicists of the day, of the Dirac's days, to learn from this that there are, sorry, I can see the words there, that there are relativistically invariant entities that lie outside the standard framework of the vector tensor calculus. And what Dirac had effectively initiated was a powerful new formalism, now known as spinor calculus, a calculus that goes beyond what had been the conventional vector tensor calculus of the day. So basically, he kind of rediscovered the spinor calculus, and I think that actually it was first discovered by Hamilton, actually, with his quaternions, and de Clifford with his algebras and Grassmann. So basically, the roots of the spinor calculus lies in there, somewhere in the like Grassmannian Clifford algebras history. Anyway, the price to pay for the remarkable elimination for the of the awkward square root was those like strange non-commuting Clifford algebra elements, those gammas. And the question we should ask, like, what do those gammas mean actually? And Penrose says here that we have to think of these things as operators acting on the wave function. And since these particular operators are new things, not directly arising from the position or like momentum quantum variables for a particle that we were considering before, they must refer to and act upon some new degrees of freedom for our particle. So, and what are those degrees of freedom, and what they describe? And the guess here is that they actually describe the degrees of freedom for the spin of the electron. And the answer is actually encoded or hidden in the name of the spinor here. And in chapter 11, we have said that a spinor may be thought of as an object upon which the elements of Clifford algebra act as operators. And in the Dirac equation, the Clifford elements act on the wave function. So it's kind of just confirms the Penrose statement from the chapter 11. And thus, the wave function itself must be a spinor. And it has extra degrees of freedom over and above the mere dependence on the position and time of an ordinary scalar wave function, and these extra degrees of freedom indeed describe the electron spin. Okay, and we will talk about that in a moment in 24.8. So basically, like the conclusion from those, defining the Dirac equation, the consequences of it was the discovery of spinors, discovery of spinor calculus, and actually I think we already had that. Like you can see that in the note number 12 that the term spinor was apparently introduced by Paul Ehrenfest in a letter to the Bartel van der Waarden, and actually in their program, as far as I understand, I kind of googled one document and I have sent that to the chapter 24 chat, which describes a bit of history about Ehrenfest and van der Waarden. And Ehrenfest was talking about the group representations in there. And I think they were thinking about spinors in terms of the physics from symmetry book. So the same way they are described in there by Jacob Schwichtenberg. And those gammas, they will correspond to the operators which will act on spinors. So currently you should just remember those basic terms, and that's it. Okay, so what we have now? What we have now is the basic theory of electron spin described by the Dirac equation, or included in there. But not only this, we also have the new power to describe electromagnetic interactions in quantum mechanics. And actually, if you will take the gauge prescriptions from chapter 19, then we will find that Dirac's electron correctly responds to the electromagnetic field as a charged electron should, including some subtle terms arising from the electron's relativistic motion. So we have also electromagnetic theory synchronized with quantum mechanics now. But not only this, we also will have the formula for the magnetic momentum for the electron, and Dirac theory predicts that it equals to this amount. And if we will compare that with the nowadays measured quantities, it's actually really close, like the mistake is 1 part in 1,000 only. And that mistake is explained by quantum electrodynamics, which actually uses and is based on the Dirac equation. So anyway, it was really like big step for the physics to get to the Dirac's equation and get the next like consequences discovered afterwards. Okay, maybe some questions about this subchapter, about spinors maybe.
What do you think he means by magnetic momentum?
Actually,
or is that an obvious question?
Yeah, I do not know. I do not know that, so we need to read more into that definition. What is that? So I can't say to you. I think for me it's just maybe like that electron has some charge, some magnetic field maybe assigned to it because it moves. And yeah, but what is momentum or magnetic moment in there? I don't know.
Maybe the force with a direction, like moment has a direction. Magnetic field also has a direction.
Have you watched Chris's video about momentum on the April 1st?
Maybe it's a while, I forgot.
Yeah, I like Chris has a really beautiful video about the definition of momentum. It's kind of a bit exaggerated, but it's really funny. So it's kind of hard to talk about, like guessing about what is the momentum without really knowing their formula. Actually, like maybe they had some tensor in there or something else. I don't know.
Well, I think that the magnetic moment of the electron or the muon or other fermions, it's related to the spin in that if you place an electron in an external magnetic field, it'll tend to align with that magnetic field, like its spin will. It's sort of like a Stern-Gerlach apparatus. A lower energy electron will more likely align with the magnetic field. And so the energy associated with being aligned or opposed to the magnetic field is related to sort of its dipole moment. Like if you had a bar magnet, there would be some energy associated with flipping the bar magnet over. And so the way that you do the calculation is you would take the dot product of the magnetic moment and the magnetic field, and that would give you the energy associated with it. So for the electron, this ends up being that magnetic moment. It's like an intrinsic magnetic dipole, or like an intrinsic bar magnet that's attached to the electron.
All right. So why do you think it's called moment?
Well, usually they do these things in expansions, and so so for example, there's like a multipole expansion for potentials and fields. So like you can have a monopole term for the electric field, and that's just like the charge. Then there's a dipole term, which has to do with two opposite charges placed in like along a line. And then there's a quadrupole moment, which has to do with four charges organized in some way. So you can actually expand fields and potentials in terms of these multipole moments. So the reason that moment comes up in there is because the geometry of it's important.
Yeah, I've took a look at the Wikipedia page, but I haven't understand like the basic definition. It seems it needs more time like to be grasped.
Yeah, I think I think he's right in that the moment basically just kind of signifies it's something that depends on like the geometry and the spatial relationship between parts of an object, and like in general, like another place that you see moments is moment of inertia, which is how hard it is to rotate something, and that just completely depends on where the mass particles or mass points are located in the object. So you could have two objects of the same mass distributed differently. They're harder or easier to rotate, and I think similarly with the magnetic moment, it's just kind of how the magnetic dipoles or particles, that have a magnetic dipole are distributed would have a different magnetic moment.
Totally, and you could actually you could do a calculation like for a really simple magnetic dipole. You can think about it as a loop of current, and so what you can do is actually like find the area of this loop and the amount of current that's going through the loop that would give you this result. And that would give you some kind of intuition for the classical version of the magnetic dipole moment of the electron. Because you can really just think about it as like an electric charge going around a closed loop.
Okay, and any other questions?
I'll just add on to what Joe and Nate were saying about the moments. Generally, if you see something with moment in the name, it's just a quantity that will describe how that thing is going to respond to being placed in a field, in this case in a field. So if it's a magnetic or electric dipole moment, that's going to basically that is going to describe how, if you place that thing in an electromagnetic field, how it's going to experience the torque. Or the same with the moment of inertia, it explains how this object, when you put a torque on it, how fast it'll start spinning. So, yeah, generally things that deal with spinning or torques or stuff like that, you'll see moment. I know in a lot of engineering, they actually will use the word moment to mean what I would call a torque when they're doing like statics and stuff. So I don't know, but you'll see it like that a lot.
Then I'm thinking angular momentum when you say that.
That definitely is the relation. I mean, the spin is sort of like a intrinsic angular momentum to it, especially if you think about it in this sort of classical picture of a charge going around a closed loop. There's angular momentum associated with that motion of going around the loop.
Yeah, all interesting, all you said.
And like, what is torque? Torque is some kind of spin or something.
It's like the angular version of force. Like you put a force on something to change its linear motion. You can put a torque on something to change its angular momentum.
Got it. So it's more about like rotation then.
Yeah, exactly. Like force, you could define force as dp dt if p is momentum. You can define torque as dl dt if L is angular momentum.
Okay, got it. Thanks. So let's go for the last subchapter. It's a bit bigger than previous ones, but it is the last. Okay, so it's called Dirac's route to the positron, and it starts with discussing the Diracs Gammas. So the question here in the first paragraph is about we have seeming mathematical anomaly in the gammas, and its anomaly is that they have 4 independent components. And we have seen spinors in the Poly form or Pauli form in the chapter 22, and we have seen that those has only 2 independent components. So the question is why and how they are connected. Yeah, and to answer that question, Penrose goes a little back into history. He says that in 1925, 3 years before Dirac published his equation, George Uhlenbeck and Samuel Goudsmit had come to the conclusion that electron must possess a quantum mechanical spin built from 2 basic spin states. And 2 years later, Wolfgang Pauli showed how to represent the transformations of these spin states under rotation by use of what we call now Poly Matrices. So we have seen those in 22.8. So they are just representation actually of SU2 group, and they are 2 by 2 complex matrices. So Pauli spinors or wave functions, they are 2-dimensional complex vectors basically. Yeah, and Pauli matrices, which are basically quaternions actually, and we know that quaternions are actually SU2 group also. They are also Clifford algebra elements, but for the 3-dimensional rotation group. So we kind of have this similar situation where Clifford algebra elements act on spinors. The same statement confirmed from the chapter 11. Okay. So, and below we have a big paragraph discussing the a strong physical need for the electron's 2 spin states. Indeed, if you take a look at the chemistry, we know that we have a notion of the orbitals there. So basically the path of the electron or orbit of the electron around the nucleus. And by Pauli's exclusion principle, it would seem that each electron orbital can be occupied by no more than 1 electron. But in practice, we find that second electron is always allowed in each of the orbitals. And the pair of them can coexist and still satisfy the exclusion principle because their states are not identical because of the opposite spins. So that's kind of the reason why we should have 2 different spins for the electrons. And the same chemical notion, sorry, not the same, but another chemical notion called covalent bond is crucially depends upon the same phenomenon actually, and you can see it on the picture here. So we have a bonding between 2 atoms here where their electrons share their 2 orbitals. So they will be kind of stuck together here. And here's a demonstration of the 2 electrons on the same orbital with different spins. Okay, so we had a bit of history, a bit of reasons from chemistry, and now we go back to the question about 4 components of the gamma matrices, I mean in terms of dimensions, and also 4 components of the Dirac's wave function. Yeah, and what we have here is just the statement that Pauli has his 2-dimensional spinors, Dirac has 4 gamma matrices, and therefore 4-component wave functions. And he says here that Dirac electron is a 4-component entity rather than just having the 2 components. Okay. And on the next page, he says that in fact there are only 2 components of spin for a particle described by Dirac's equation. despite there being 4 components for the wave function. So mathematically, the reason for this is closely related to the fact that Dirac equation is a first-order equation, and its space of solutions is spanned by only half as many solutions to the original second-order wave equation, Klein-Gordon equation. And that equation is also satisfied by the Anti-Dirac equation. And physically, this counting of the solutions of the Dirac equation must take into account the fact that the degrees of freedom of the electron's antiparticle, namely the positron, are also hidden in the solutions of the Dirac equation. So it would be misleading. And he says, so like basically we can just condense that paragraph into like statement that Dirac's spinor is actually kind of 2 Pauli spinors in one, because it encodes both of the antiparticles. Kind of like that. But at the end of that paragraph, Penrose says, it would be misleading to think of 2 of the components of the Dirac equation as referring to the electron and the other to the positron. So it's not really so simple, and we will see in chapter 25 about the exact nature of electrons, and we will talk more about what those Pauli spinors, 2 Pauli spinors, are actually describing and how they are related to the antiparticles. So things are very much more subtle than this and not so trivial. Okay, so that's kind of I think that was the end, right? Yeah. So that's kind of the end of discussion of the 4 components of the Dirac spinors, and we will continue about we will continue talking about spinors in chapter 25 at the beginning of it. So anyway, now we can go back to the theme discussed at the beginning of the chapter 24 about negative energies. So, and recall that we wanted to get rid of the negative frequencies, negative energies, solutions to the Schrödinger equation. But it turns out that solutions to the Dirac equation are not restricted to having only positive frequencies, so they can have the same problem with the energies in there. And yeah, so, and it will not cause a lot of problems with non-interacting particles, but even if you will have like small interaction like with electromagnetic field, it will cause initially positive frequency wave to pick up negative frequency parts. And Dirac kind of been thinking about that, and he decided that if negative energy states exist, then electron could fall into such a state with the emission of energy, and if there is an unlimited number of such states, then there would be a catastrophic instability. So everything will kind of just fall into those negative states infinitely, with infinite amount of energy kind of delivered. And all electrons tumble into the negative energy states of greater and greater negative energy with emission of more and more energy. So it would be kind of catastrophic results for the real world. But Dirac reasoned afterwards that electrons satisfy the Pauli exclusion principle, and it is not allowed for such a particle to occupy a state if that state is already occupied. So he made the astounding suggestion that all the negative energy states should be already occupied. This ocean of occupied negative energy states is referred as Dirac Sea. Therefore, according to Dirac's crazy idea, we indeed have the fulfillment or filled up negative energy states, and by Pauli principle, there is now no room for an electron to fall into such a state. And we can reason further that occasionally we could have a situation where, for example, some I think like something will cause the electron to leave its state in terms of like negative energy. So occasionally there might be a few negative energy states that are unoccupied. So what would happen then? He says here that like such a hole in the Dirac sea of negative energy states would appear like a positive energy particle, and hence a positive mass particle whose electric charge would be the opposite of the charge of the electron. So we are coming here to the basically theory of the positrons as those holes, and you can see a picture at the top of that page that we kind of can see those energy states as a big C of the electrons, which are already at the those negative energy states which are occupied by them, and we can now think about annihilation and creation operators or like events which we talked about at the beginning of the chapter as the disturbances of that Dirac sea. So at the picture A here you can see annihilation process where positron, that hole, an electron, like electron got into that hole, it kind of fills it up, and afterwards some energy is released. So that's annihilation process. And the creation process is here, so we apply some energy, maybe some photons are going to bump into the electron here, and then electron goes from its previously occupied negative energy state, and flies out, leaving the hole opened here. And I still do not get one small thing here. So he says that like the occasional unoccupied state, a hole in this negative C, would appear as an anti-electron or positron, thereby having positive energy. So like my question is why we can reinterpret the hole as a particle, and why if hole is the negative energy state, then that particle will have positive energy state. So I have this question and I have no answer for it. Maybe someone can comment on that.
Sorry, is your question why the hole is a particle, or why the hole has an energy, or what was the exact question?
Yeah. So Penrose says that we can think about that hole as a positron. And like we know that this hole is kind of the possibility for electron to get to the negative, like to fill up the negative energy state, right? And the question is why we are thinking about that hole as a particle. Maybe that's the one thing. Like, so maybe we can just identify the hole with a particle. So let's call that hole a positron. Okay, but why that positron will have positive energy instead? So why?
So I'm not. Sorry, I'm not sure about all the details. I remember taking a sort of like a semiconductor class, and they kind of do treat, like if you have like a silicon or something like that, there might be like some charged particles like inside the silicon like layer or whatever, and I think they do treat holes as if it's like a particle can kind of fall into it. That's almost like a positive and a negative canceling out and you getting a neutral.
But electron also has positive energy, right?
Yeah, I guess so. I guess I don't understand that.
Well, so let's look at this leftmost picture here. So the electron that's on the right side of that hole, if that electron moves to the spot where the hole is, it's as if the hole has moved over to the right. And this could happen over and over again, but the energy exchanged is actually the same for the electron moving to the left or the hole moving to the right. And so the energy that's exchanged as the hole moves around is the same as the energy of the electrons moving in the opposite direction. So it truly does behave like a particle. You could imagine this hole like moving around, but it's there's no like actual hole that's moving around. It's the particles around it filling the hole, which opens up a hole in another place. But the energy that it took for that particle to fill the hole is just the energy that it took to create the hole in the next place. So it's very much like the hole is actually moving around, and it's got the same mass as an electron and the same charge, or opposite charge.
Mm-hmm.
Yeah, it seems like it's almost exactly like the semiconductor thing where, you know, they talk about a hole moving around, but you could also just say it's a positive charge moving around, even though technically it's electrons moving to a hole, which creates a hole in a new spot and kind of effectively moves the positive charge around.
Yeah, and so the major distinction there is like the hole is moving to the right here, or the electrons are moving to the left, but the energy exchange for those processes are exactly the same.
Yeah.
Then my question would be that, so for the sea of electrons that are occupying the negative energy, so the electrons around the hole, they all have negative energy, right?
Yeah. So I think we should think about the negative energies as actually like lower energy states, just lower. So like it's really relative in physics, like when we are talking about negative or positive energies.
But I'm not sure about that because, sorry, echoes. Because I think I can understand that potential energy to be relatively high or low, and you can set arbitrary zeros. But for example, how would you have like a negative momentum energy? That is, I don't know how to think of that.
What you meant about negative momentum energy?
So I'm not understanding like how would a particle with a negative energy would behave. For example, the C, so the particles around, the electrons around this hole have a negative energy, but the electrons with a negative energy can still move around. That is what I don't quite understand, how an electron with a particle with a negative energy would behave.
Like my intuition here is something like that. So you kind of have like a potential well, and you have your electrons like tumbling down at the bottom here, and you have some reference level the same way in the like in gauge theories, you know, like we have like 0 here, for example, and we can say that those electrons are in negative energy states, but we can like put maybe that 0 even further down, right? So it's interesting if we can prove that we have that like bounding from the bottom. Is that possible or not? So I don't know if we can prove that we have a nice lower bound on that.
I think there almost certainly is, and it's great that Yuri brings this up because she's working in statistical mechanics. You know, like the thing is that there is an absolute 0 temperature, and so if you change this energy scale to go negative, then you could have like negative temperatures as well. Like if you try to relate this to thermodynamics, so it's not like you have some gauge freedom in choosing the lowest energy state. It's that, you know, we actually don't observe negative temperatures, and we actually also can't get to absolute zero.
So therefore, we can kind of shift that zero to the bottom and say it's the bottom. It seems so.
Right.
I think this is like kind of an outdated idea. Like I think this was what Dirac came up with when he was first grappling with the concept. I think the modern view is just particles and antiparticles.
Yeah. I think we will see. We will see. Anyway, so I can say that if you want to have more information, you can just take a look at some articles about Dirac C and read about holes. So I will probably do that for the next time. Okay, so that's basically the idea behind the positron. So and the last paragraph of the subchapter 8 is about like the psychology of the science actually. That and actually Eric talks about that case like often in his interviews, often in his papers or paper about geometric unity. He definitely says about it there that Dirac was actually cautious about making the claim that his theory actually predicted the existence of the antiparticles to electrons, initially thinking that the holes could be protons. And nevertheless, the theory was actually kind of clear that those holes should have mass of the electron, and mass of the proton, we know it's about like 1,800 times larger. So Dirac was kind of really careful in there, but like Eric says that maybe we shouldn't be too much careful. Like let's play around with the stuff. So it's kind of the basic idea here is that Dirac believed into positrons only like in a few years, basically. So when Carl Anderson announced the discovery of a particle which indeed had the properties that Dirac had predicted, it was the first antiparticle which had been found. And it was like 1932 probably, like next year.
Ja, want hij won de Nobelprijs.
Yeah, so that's it. In terms of the spinor dialogue or like spinor research, I think the note 12 here is really interesting. So I think it would be interesting to see what actually Paul Ehrenfest called spinor when he first coined the term. Yeah, so that's it with chapter 24, and as my estimates confirms, it's currently mid-May, right? Or even not mid-May, even 1 week earlier. We approach the chapter 25, and we will start with it on the next call. Let me see. Yeah, I think we will. We should take a look at the first 10 pages. So let's start from a small part of it. I think it would be enough for the next time, or maybe, or a little bit more, maybe till the 25.5, because 24 or 25.4 is pretty small thing about charge conjugation, parity, and time reversal. So I think we can read till the 25.5, can see it, yeah, till this place for the next time. It will be like 12 pages maximum.
Sounds good to me. Thank you, Slava, and thank you everyone else for the discussion.
Yeah, welcome. maybe more questions, more propositions, more comments, anything?
Well, I have a comment because I know Chris is quite interested in chirality. So that means we're 2 weeks out from chirality. Whenever we get to the 25.5.
Cool, good to know.
Yeah, I think it never hurts to run a bit forward, so Chris can read 25.5 for the next week if he is really interested.